I am Dr. Abhishek Joshi, and in this video lecture I am going to discuss about digital receiver performance. Now let's start. So in this lecture I am going to discuss about the digital receiver performance, that is the introduction, the BER. Then we'll be discussing about the probability of error in optical communication, then the receiver sensitivity, the quantum limit, and point-to-point link. Let's start. So digital receiver performance. So the basic performance parameter for identifying the digital bits, that is in form of zeros and ones, because in optical communication we are using the digital communication. So bits are represented either in form of 0 or 1, or we can say the voltage level, that is the output voltage level. So in this, the first performance parameter is the BER, also known as bit error rate. So a simple approach is to divide the number, that is the number of errors occurring in a certain time interval, that is the duration of the bit in an interval. Let's say the duration is t. For the entire bit duration, like 1 0 1 1 0, like this, and we have the total number of bits. So for example, if we have 100 bits, total bits, that is, and t is number of 100 bits, and out of 100 bits we are having 1 bit error. So number of bits are having error is 1. So we can calculate the bit error rate. So bit error rate will be given by, that is BER, will be given by, that is NE, that is bits having the error, number of bits having the error, divided by total number of bits, that is NT. So we know that, let's take this example. We are having 100 bits, total number of bits are 100, and 1 bit is having error, so it will be 1 by 100. Practically, this value is very small. So simple approach is taking the ratio, that is NE by NT, and for zeros and ones we calculate, and this is called either the error rate or the bit error rate. So where B representing, so we can also represent in terms of the bit rate, that is BT, that is given by 1 by TB, and that is a pulse transmission rate, and the error rate is expressed by the number such as 10 to the power minus 9. So this is a practical example. So for example, which states that on an average 1 error occurs every 10 raised to the power or every billion pulses, 10 to the power 9 pulses. So typically error rate for the optical fiber telecommunication system ranges from, that is, it's ranging from 10 to the power minus 10 to 10 to the power minus 12. So this is the typical value of the BER, that is bit error rate. So this error rate depends on the signal to noise ratio at the receiver, that is the ratio of the signal power to the noise power, and that is the system error rate requirements and the receiver noise levels. Thus, a set of the lower limit on an optical signal power level is required at the optical photodetector. So the probability of error, we can calculate the probability of error by taking the area under the curve of the probability distribution. So to compute the bit error rate at the receiver, we have to know the probability distribution of the signal at the equalizer output. Knowing the signal probability distribution at this point is important because it's here that the decision is made as to whether a 0 or 1 is sent. The shape of these two signals, that is having the probability distribution given by P. So probability distribution for 1, because we know that bits are either represented in terms of 1 or 0. So for probability distribution for 1 is given by P subscript 1, and V is the voltage. So we have to take the area under the curve. For area under the curve, we'll take the integration from minus infinite to V. Let's say take some threshold voltage, that is V. So it is given by the probability that bit Y has been received, what was transmitted. So 1 was transmitted and bit Y is received. So we are taking the integration with respect to dy. So which is the probability that the equalizer output voltage is less than V when the logical 1 pulse is sent, and we have the probability distribution for logical 0 is sent, that is given by probability V subscript of 0, and V is the voltage, integration from V to infinite, that is the threshold voltage, and the probability that Y, that is 0, is transmitted and Y bit is received. Y may be 1, it is having the value 1 or 0. So which is the probability that the output voltage exceeds the V? V is the threshold voltage when a logical 0 is transmitted. And note that the different shapes of the two probability distribution, that is in the figure which is in the next slide, we can see here we are having the probability distribution for the 1 has been transmitted and 0 has been transmitted. We can see these two pulses, and this is the threshold voltage. So if we have the value above the threshold voltage, we'll see that 1 is received. If we have the value or the received value less than the threshold voltage, we'll say that 0 has been received. So this is the probability distribution. It is more or less the Gaussian distribution, which is having the threshold voltage, that is P0V and P1V. So we can understand in the time domain, we are having the pulses. If it is a 0 level, so 0 level, the received bit has having the 0 level. It is below the threshold voltage. Let's represent it by VTH. VTH is the threshold voltage. If you have the value less than the threshold voltage, we will see that the 0 level or the 0 is received. Otherwise, we are having the 1. Okay. So because it is above the threshold voltage. So same concept is used for identifying the error in the optical communication, same as the digital communication. So this indicates the noise power for the logical 0 is usually not the same as the logical 1. So this occurs in the optical system because of signals having the distortion from the transmission impairments, that is the dispersion, optical amplifier, noise, and the distortion from the non-linear effects. Non-linear effects we have covered in the previous lectures, that is that it may be a Kerr effect, okay, and from the noise and ISI. ISI is standing for the inter-symbol interference contribution at the receiver, and the functions, that is Py by 1 where 1 has been transmitted and Py by 0 where 0 has been transmitted, are the conditional probability distribution function, that is Py by x. So it's the probability that the output voltage is given by y, and we have transmitted x. X was a transmitted bit. So if the threshold voltage is given by VTH, then the error probability, that is PE, is defined as, the probability of error is given by A times P1 VTH plus B times P0 VTH. So we have covered this, that is the distribution for 1 and distribution for 0. That is the probability distribution for the received logic 0 and 1 signal pulses, and the different widths of the two distribution are caused by the various signal distortion effect. The weighing factor A and B are determined by the priori distribution of the data. That is, A and B are the probabilities for either 1 or 0 occurs respectively. For unbiased data with the equal probability of 1 and 0 occurrence, that is A equals to B equals to 0.5, which gives the probability for 1 and 0 are equal probable, that is 0.5 or 1 by 2. So the problem is to be solved now is to select the decision threshold voltage at the point, that is where the error is minimum. So here we can see the error is minimum here in this region, but here we have the overlapping region which may cause the error. So BER, or you can say the bit error rate, is given by the probability of error for the Q function, that is PEQ 1 by under root pi integration Q by under root 2 to infinite e raised to power minus x square dx, and that is equals to 1 by 2 1 minus ERF Q by under root 2 1 by under root 2 pi e raised to power minus q square by 2 by q. So the approximation is obtained from the asymptotic expansion of the error function, that is ERF of x. Here the parameter q is defined as, So Q function is defined by the threshold voltage minus the bit off. So bit off is nothing but 0 divided by the variance of off. That is also equals to, we can calculate for bit on is nothing but the level 1, the threshold voltage, if you are taking at 0 and 1, so threshold voltage will be obviously 0.5. If you are taking -1 and +1, the threshold voltage will be 0. So if you are taking -1 +1, threshold voltage is given by 0. If you are taking for +1 and -1 as two levels, if or otherwise we can take the threshold voltage as 0.5 if we are using 0 and +1. So depending on that, we can choose the threshold voltage. So B on minus VTH divided by the variance of on, or we can directly write that is the bit on minus bit off divided by variance of on and variance of off. So we can define the error function that is ERF of the transmitted bit X, that is given by, that is 2 by under root pi integration from 0 to X e raised to power minus y square dy. So we can see here the bit error rate versus the Q factor. So we can see that as the value of the Q increases from 0 to 8, the probability of error is decreasing. So here we can see the probability of error is equals to 10 to the power minus 9 for the Q value, where the Q value is 5.99. So here we can see the Q value, that is 5.99, and we are having the probability of error given by 10 to the power minus 9. So this is a plot of BER versus the Q factor. So next topic is the receiver sensitivity. So optical communication system use a BER value to specify the performance requirements for a particular transmission link application. So for example, we are having the SONET. SONET stands for the synchronous optical network, where SDH stands for synchronous digital hierarchy. So these are the two networks which are used as an extension of optical communication, and this network specifies that the BER must be 10 to the power minus 10 or lower, whereas the gigabit Ethernet, which we are using as a internet, and the fiber channel requires a BER of no more than 10 to the power minus 12. So we can see that if we are using the optical communication, we are having the BER of 10 to the power minus 10, and if we are using the Ethernet, we require a BER of 10 to the power minus 12. To achieve a desired BER at a given data rate, a specific minimum average optical power level must arrive at the photodetector. So the value of the minimum power level is called the receiver sensitivity. So we can see in this figure, we are having the bit error rate as a function of signal to noise ratio when the standard deviation are equal, that is sigma on is equals to sigma off, when that is bit off is equals to 0. So we can see that is a voltage divided by the standard deviation. Here we have on the x-axis ranging from 0 to 10, and the y-axis is having the bit error rate. So that is BER, or we can say it is nothing but the probability of error. So we are having probability of error that is given by PE, that is equals to 1 by 2 1 minus ERF V by 2 under root 2 sigma, that is the standard deviation. So we can see that as the voltage standard deviation is increasing, or you can say the signal to noise ratio is increasing from 0 to 10, the probability of error, or you can say the bit error rate, is decreasing. Similarly, we can see the other curve. The next topic is the quantum limit. So in designing an optical system, it is useful to know what the fundamental physical bounds are on the system performance. So let us see what this bound is for. the photo detection process. Suppose we have an ideal photo detector which has a unity quantum efficiency and which provides no dark current. So that is, we don't have any dark current. So we can see this bit rate versus the sensitivity. So on the x-axis we are having the bit rate. Bit rate is ranging from 0 to 10 and with a step of 0.01, and we can see here the sensitivity is increasing. So sensitivity on the y-axis in decibels, millidecibels, and it is ranging from -20 to -50, and we are analyzing two types of receivers, that is PIN photodiode and avalanche photodiode. So we can see that the sensitivity of PIN photodiode for the bit rate, that is from 0.01 to 10, we are having the higher value, and for the avalanche we are having the lower value in case of the sensitivity. So these are the sensitivities as a function of bit rate for the generic PIN and PIN diode, and the avalanche photodiode, that is for the indium gallium arsenide photodiode at 1550 nanometers for 10⁻12 BER, that is bit error rate. So the electron hole pairs are generated in the absence of the optical pulse, and given this condition, this is possible to find the minimum received optical power required for a specific bit error rate performance in a digital system. So this minimum received power level is known as the quantum limit, and since all the system parameters are assumed ideal and the performance is limited only by the photo detection statistics, assume that an optical pulse of energy E falls on the photo detector in a time interval tau. This can only be interpreted by the receiver as the 0 if no electron hole pair are generated with a pulse present. So we have the probability that at n equals to 0, electrons are emitted in a time interval t, that is given by PR of 0 e raised to power minus n, where we have n bar is nothing but the average number of electron hole pair, that is given by n bar. So for a given probability of error, that is PR for 0, we can find the minimum energy E required for the specific wavelength, that is given by lambda. So next is the point-to-point link. So point-to-point, when we want to establish a link between a transmitter and the receiver, we have to consider few points, that what should be the source. It may be LED or laser. What should be the receiver? It may be a PIN diode or the avalanche photodiode. What should be the optical fiber? So all these parameters, when we are considering for establishing a point-to-point link, is discussed here in this slide. So we have the simplet transmission link is a point-to-point line that has a transmitter on one end and a receiver on the other. So this type of link places least data demand and optical fiber technology, and this sets the basics for the examining more complex system architecture. And the design of the optical link involves many interrelated variables among the fiber and the source photo detector operating characteristics, so that the actual link design and the analysis may require the iterations before they are completely satisfied, since the performance and the cost constraints are important factor in the fiber optic communication link. So that's why we are analyzing these parameters, and the designer must carefully choose the components to ensure that the design performance level can be maintained over the expected system lifetime without over specifying the component characteristics. So there are a few key system requirements. The first one is the desired or the transmission distance, second one is the data rate, and third one is the bit error rate, that is BER. So in this we have to first examine that which fiber we need. It may be a multi-mode fiber or the single mode fiber. What should be the core size? What should be the core refractive index? What should be the bandwidth or the dispersion, the attenuation, and the numerical aperture? So these parameters we have to identify, then only we have to decide that which fiber we have to choose. So we have the basic block diagram is having the information source. We have the optical transmitter. It may be LED or the laser. Next is the optical fiber. Then we have the optical receiver. And last one is the user. Next is the source, that which type of source we want to use in our for establishing a link. So LED or the laser may be used. We have the emission wavelength, the spectral line width, the optical power of the diode, the laser diode or the LED diode. What should be the effective radiating area? Next is the emission pattern and the number of the emitting modes. Next is the avalanche or the PIN photodiode. So what should be the responsivity? What should be the operating wavelength? What should be the speed? And what is the sensitivity for the PIN and the avalanche photodiodes? So to analyze usually are carried out to ensure that the desired system performance can be met, and these are the link power budget and the system rise time budget analysis. So in the link power budget analysis, one first determines the power margin between the optical transmitter output and the minimum receiver sensitivity needed to establish a specified BER, and this margin can be allocated to connector, splice and the fiber loss, plus any additional margin required for the other components, the possible component degradation, the transmission line impairments or the temperature effect. So if the choice of the components did not allow the desired transmission distance to be achieved, the components must have to be changed or the amplifier have to be incorporated into the link. So once the link power budget has been established, the designer can perform a system rise time analysis to ensure the desired overall system performance has been met. So we shall examine the analysis in more detail in our next lecture. So in this lecture, we have discussed about the digital receiver performance, the bit error rate, BER, probability of errors, the receiver sensitivity, the quantum limit and the point-to-point link. So here we are going to end this lecture. Thank you.